People are still working in. Good afternoon. Welcome back to the ballroom this afternoon. And yesterday at the keynote session, In Hee Su from IBM, she presented her view on cognitive computing and the future in the era of Industrial Revolution 4.0. And basically, she looked at the world as a planet powered by billions of industrial Internet of Things. And because of that new technology, it will literally change the way we do business, something that she called the art of the possible. In that everything that we do, we could change our business model. But in order to make it happen, there is the other side of the coin is how to build a new cyber infrastructure that is beyond the cloud computing that we are talking nowadays. We need something that is much faster hardware, more powerful software, more robust network infrastructure, and therefore we need something that is exponentially much more than what we have today. So this is basically what we are trying to achieve in the second keynote. So John C. Brown and I, we were discussing about who would be the best guy to do this kind of thing. And the more we talk about it, the more we thought that nobody else but Larry Smarr would be the best guy to share his vision about the new cyber infrastructure to us. So who is this guy? Again, for those who haven't met him, this guy actually, the more I talked to him, the more I got so impressed. I guess the easiest thing to do is to Google him. Or a little bit easier way to do is to look into the bio that we put in the conference brochure. Even we add only a few lines of his life, it's so impressive to see how much achievement, awards, and everything that he has put together and his contribution to society. But beyond those official and professional recognition, I have learned quite a few interesting things about Larry that I would like to share with you a little bit. Probably the hottest and most breaking news about his reputation is that you must have learned in the news that Kip Thorne and two other people earned the Nobel Prize in Physics this year. And their work is on estimating the radiation when two black holes collide using Einstein's equation of relativity. And then when Kip Thorne presented his presentation when he received the prize, he had a picture showing a young Larry Smarr with a ponytail hair and naming and recognizing him as a team contributing to the success of his work, leading to a Nobel Prize winner. So that is actually quite a recognition. Another thing that impresses me about Larry is his choice of hobby. He was, in his earlier life, he was a professor of physics and astronomy. So let me ask you a question. For a guy, a professor of astronomy, who likes, among other things, going to Hawaii, what kind of hobby would he like? Would he like? A professor of astronomy going frequently to Hawaii. Whale watching, sailing, stargazing. This is what I guessed, but you and I were wrong. The guy actually likes snorkeling, and he has done that for, he has done that for 30 years. And then, but the most appropriate thing for me to talk about Larry this afternoon, since he's giving a talk on creating a global research platform for big data analysis, is that Larry himself, as a human, has made himself a data generator. He has a sensor over here to collect his temperature. He has a wrist appliance here to collect his vital sign. He takes sample on his DNA every day to do data analysis. And the second question for this afternoon, guess how much data does he collect on a daily basis on his own body in order to do data analysis? 1,000, 10,000, 100,000, 1 million? Could you give me an idea? 100,000, 100 million. One more guess. 6 billion data point regarding his data with his DNA related information. So this is really the concept of big data in the context of what he's doing. So with no further ado, please join me to welcome Larry Smarr, the second keynote of the day. And I have a pleasure to invite Angela, the youngest and newest doctoral consortium fellow of HICSS conference, to hand over the lead to Larry.
Well, thanks very much to you, Tong, and to John Seeley Brown, who has been a very trusted and inspirational advisor to me for decades. One of my advisors at Cal IT2. I was giving the keynote for HICSS 7 years ago on the collaboration technologies that we've developed over the years. It's amazing to me, thinking back on that and looking at the talk I gave then, that most of what I'm going to talk about today didn't exist, and I had no idea was going to exist, and yet it's changed everything. So what I'm going to talk about today is what I've actually been personally involved in for over 30 years, which is trying to imagine a way to build a distributed system that acts as if it's in a single place. And the reason we need to do that is because in the world of data, the data is being generated everywhere. And the idea you're going to take it all, put it in one big bucket in somewhere near a big computer, that's 20th century thinking. Now, 30 years ago, there was a historic moment when NSF took the torch from ARPA and took the ARPANET technologies that Vint Cerf and Robert Kahn and others had developed and created the NSFNet, connecting the 5 new supercomputer centers that it created in 1985. I was the PI and director of NCSA in Illinois with NCAR, the NSF Center for Atmospheric Research. Now, it's hard to imagine, but the big shared internet pipe across the country at that time was 56 kilobits a second. What we later knew as a dial-up modem. What I'm going to talk about today is a world that's about 2 million times that bandwidth. But the important thing is, when you have the wide area network so low compared to so many orders of magnitude less than the backplane of the computer that you're on, effectively you have compute and data islands that are separated, like the Hawaiian Islands, from each other. And you're essentially using outrigger canoes to get between the islands. 10 years later, when there was a company called MCI, you may remember, who provided the network to create what was called the very large, the VBNS for high bandwidth. And this had gotten up from 56 kilobits to 1.5 megabits to 45 megabits to 155 megabits, 622, and so on, up to, it was just about in the late 90s to go into the first gigabit. But again, the NSF was looking at how could we connect all of the people who in those days they still thought needed to get to supercomputers. And so they created a program where they shrank the number of supercomputer centers to 2, San Diego Supercomputer Center and the one I ran at NCSA, and then had vast numbers of partners that were connected, including distributed data and computing. But again, this was connecting to the campus gateway. And if you're in the third story of a building on the campus, good luck in terms of your bandwidth to the actual computer or the data. So the vision that we had even back then was, with the emergence of fiber optics, which have a capacity to move data at terabits per second, there was no real reason why you couldn't have the wide area network faster than the backplane of the clusters you were connecting. In other words, you would have then a tightly coupled. Now, I'm a physicist originally, so I think of materials properties. So spring steel is tightly coupled material, whereas something like rubber is very weakly coupled. And the speed of sound actually in those materials, it works the same way. It's much higher in the tightly coupled systems. But the idea was we could actually create a national, even global scale computer that acted as if everything was in the same rack. So in other words, if you think about the bisection bandwidth of a cluster being gigabits per second, for instance, now imagine that over the whole country or the whole world. And that was technically possible. And indeed, NSF 15 years ago, we put in a proposal of his PIF called the Optoputer that said, look, can we at least do a breadboard of this? Can we actually show that it's possible? And that was the so-called Optoputer project, with the IP being Internet Protocol, coupling optical fibers with computers. And we actually did this. It was a collaboration not only with multiple universities, but with multiple companies, including IBM, for instance, and with a number of countries like Japan, Korea, the Netherlands, and so forth. And the idea was that you could bring together not only the video streams that were just emerging at that time, HD and of course now 4K, but also all of the distributed computers, clusters, scientific instruments, and put them all through an optical switch and then into a scaled up portal that would both scale up the visualization for analyzing the data visually, but also scale up the storage, scale up the computing, and so forth. And so this was a slide actually from 10 years ago, basically. And it was working. So you might say, well, if that was going on 10 years ago, how come we don't have it today? How come you're telling us you're building it in the future, not the past? Well, oddly enough, the director of NSF at that time, Arden Bement, understood what the problem was. We had wide area networks, but they were to the campus gateway. And as Arden, which was quite actually future-looking for an NSF director to say something like this, he said, you know, basically we've got like the interstate highway system, 6-lane highways across the country, but when they get to the campuses, they become 2-lane roads, or even sometimes said dirt roads. And so the problem is on the campuses into the final end-to-end to the end user who's in some building somewhere with some computer. Well, notice that was May of 2005. So what happens when the NSF has something like that, they set out a blue ribbon task force of folks, and I was on one of these panels that produced this study called Campus Bridging, and that came in 2011, and it was brought to the NSF as the community input. And amazingly enough, NSF put in place a program, and I don't know how many of you know about this program, the Campus Cyber Infrastructure. How many of you have gotten a grant on your campus or been involved in the US, of course? 1, 2, 3? This is the largest investment by the National Science Foundation in networking on campuses in the history of this country. It's never been anything remotely like this. And it is a complete step function in terms of the capacity that we now have. But most people don't even know it happened, and it's almost over. Here's what one looks like on our campus at UC San Diego. You have a switch, in this case an Arista switch, that is capable of switching very many of these 10 gigabit per second streams. And when I say 10 gigabit, that's 10,000 megabits a second. So how many of you experience as a user 10 megabits a second over the internet? Okay, how many 20? How many 50? How many 100? Okay, so where we're going to is 100,000 megabits per second. That's 100 gigabits per second. And across our campus, we have that working. So we have 120 gigabits per second that connect the San Diego Supercomputer Center with my institute, the California Institute for Telecommunications and Information Technology. We have 10, 40, 80 gigabit per second clear channels to end users and their instruments, their genome sequencers, their microscopes, their computers. Now to put that in perspective, there are 30 or 40,000 users of the shared internet on our campus. And all their traffic, including all the students watching Netflix, go through one 10 gigabit per second fiber optic. And now I'm going to give it to you, and just you. So that's the kind of jump we're talking about here. Now, if I come to you and I say, it's your lucky day, I'm here, here's your fiber optic, you're now going to get 1,000 times as much data per second into your lab as you have been used to. Good luck. And the first thing, you look at this thing and you say, well, where do I plug that into? I've got all this blue wire around here, which is copper, Cat6, Ethernet. I know I got all kinds of plugs into my computers for that, but where do I put this fiber optic? So that was the next thing we had to fix. So we've now gotten the wide area, we've gotten the local area, and now we have to terminate it. And so you know how any networking system works, the engineering that goes into, say, the cell phone. Nothing in the cell phone is engineered beyond what the Wi-Fi and shared and the commercial internet, wireless internet can bring in terms of data. Because otherwise, why would you do that? So the same with your PC. This PC is configured and engineered to handle essentially the shared internet. And the shared internet is basically about putting photographs from, cats on, apparently. This seems to be aliens came down and looked at planet Earth. There's cat videos. That's what the internet was built for. So you got anything bigger than a cat video, you're out of luck. Because that's what the world invested in, was an infrastructure to handle cat videos. So if you've got gigabytes to terabytes, don't think about using the internet to send it across, okay? It's going to take forever. That's what we had to deal with. So we're now giving you 1,000 times the bandwidth, but we've got to be able to terminate that flow, that fire hose, right? But amazingly, what my colleagues and I have done for 30 years is just ride the commercial product space, and in particular personal computer-driven space. And so these are actually just personal computers, whether they're desk side or in racks, but they may have, say, 100 terabyte rotating disks, they may have 6 or 7 terabytes of flash, they have 10, 40, 80, or 100 gigabit per second network interface cards, so they can terminate optical flows at that speed, and then they have very large RAM. But they're PCs, and so they're very inexpensive. And in fact, if all you want is 1,000 megabits per second, we can give you that for a few $100s now as a termination device. I mean, it's really amazing. I don't think we sometimes appreciate the magic of the world we live in. Each of these PCs has has like 100 times the memory of a Cray 2. 100 gigabytes, something like that. That cost me $15,000 when I bought a Cray 2 in 1988, I had to build a whole building to put it in. So by using the commercial technology, we're able to make these so inexpensive that you basically use your supply budget Now, how does that transform the doing of science? Well, here's an example on our campus where Rob Knight, who is one of the leaders in the world in the microbiome, which is very big data. I'm giving a keynote talk tomorrow at a conference up the beach at the Pacific Symposium on Biocomputing on the microbiome. Vast amounts of data. To put it in perspective, 90% of the cells that have DNA in your body are not human. And they have DNA in them, and the human cells have DNA, the cells that have DNA, is 10 to 1. But if you ask how many genes are there on the DNA in your body, there's something less than 25,000 genes on your human DNA. There's about 2 million genes on the microbes. So you're talking about 1/10 of 1%, basically. And so that, it changes. I mean, think about medicine. It's dealing with 10% of the parts and 1/10% of the genome by looking at the human. How well do you think that's going to work out? But in the next 5 years, because of the big data revolution, all of this microbiome data is going to come to the world. So what we've got is one of these Fionas, the flexible I/O network appliances that we call them, these PCs in Rob's lab, connected across these 10 gigabits to the Genome Sequencing Center, and from there over to my institute where they can use the big wall to look at 50 times the resolution of your laptop for visual data analysis, and then over to the San Diego Supercomputer Center, which has by now over 10 petabytes of storage, but then it has these big supercomputers that are optimized for big data analysis. And so Rob's Center for Microbiome Innovation can also then reach out to the NIH, for instance, the National Database on Microbiomes. And so this is the infrastructure which he's now doing his research on, compared to just being one of 30,000 people running across the internet and trying to get his data from point A to point B. To put that in perspective, Rob and I are burning a CPU century per year on the supercomputer just to analyze the microbiome data. So that's over 1 million CPU hours. So run your computer 24/7 for 100 years. We use that much computer time every year. So we got a lot of data that we have to look at. I must say I'm very pleased to be with Rob and my colleagues at UCSD, part of a new IBM Cognitive Horizons network. We're one of the, I guess we're the newest member of as a university, studying, helping tutor Watson in healthy aging, but also in the microbiome. So by the time we're done, we will have brought in all of this microbiome information into Watson so that its ability to help in healthcare will be greatly increased, we hope. So the next logical step is, given that we have over 100 campuses that have this campus infrastructure, none of which had it when I gave my last keynote here. It's hard to believe how fast things have changed. But the obvious next thing is, well, can we hook them all together? And so I wrote a proposal with my colleagues called the Pacific Research Platform, which has now been funded at $1 million a year for 5 years. And it hooks together essentially all the research universities on the West Coast. So that's all of the 10 UC campuses, one of the Cal State campuses, Stanford, Caltech, USC, the 3 privates, as well as national labs, NASA Ames, Lawrence Berkeley Lab, and then up to the University of Washington. But then we also extend out to Chicago and to Hawaii, and then beyond that to a few international partners I'll end with. And the idea is to make this all hooked together as one big optically connected computer, in which basically you have this enormous speed. Well, to do something like this, remember, $1 million is about 3 FTEs. So So, but we have this amazing, this is one of the largest volunteer projects in US history that the NSF has run. So we have over 50 different campuses, CIOs and IT leadership, as well as 32 of those, 50 researchers. All of these are scientific researchers that are on leading edge computing, big data science applications. And none of them are getting paid from this grant. They're all doing it because they think this is the future. Okay, so now what we do is we create these terminating devices, these Fionas, and we drop ship them all over the place. So we've got like 30 of these or 40 of these that have now been put out there. And then 4 times a day, we do end-to-end measurements, disk to disk, of 10 gigabyte file transfers. And then we measure with a variety of software tools, hardware tools, the throughput, disk to disk. Now, this is an unnatural act. Nobody who runs the networks is in charge of the end-to-end network. So in your building, the department controls how you do the networking. On your campus is the campus CIOs. Then you got your regional optical networks. Then you got your national internet twos, your international networks. There is no entity in charge of the end-to-end. There's who you going to call? Ghostbusters, right? Who are you going to call? And so that's why we decided, okay, we'll make it our business. So we put together a distributed team of probably 30 or more of the best network engineers on the West Coast who every week for an hour have a phone call to debug this. And you'll notice that when we started, we had everything was orange, which means you can't even get the data across. Now we have many, many more, and they're all green, which means they're doing more than 5 gigabits per second disk to disk. Now, one of the big software revolutions, once you've sort of got this hardware end-to-end set up, so you've got the terminating devices, you've got the networks, now you've got to put software over all of this, right, to make it act like a single computer. One of the great innovations that Fernando Perez at Berkeley has developed, first was Python and then is Jupyter. So these give you electronic notebooks, which are just the web for software and data. So in other words, you have live software, your data is live, the visualizations are live, and if you just give somebody a URL, then that notebook is now on your machine, and you can execute. You just click on it, and the software executes. The data you can pull out and put it into your code and so forth. It's a real revolution, and it is the basic paper, that we are doing digital sciences on. So it's been a huge revolution. And so the first thing we did is they said, okay, well, we have to have that software across the Pacific Research Platform. So we made a big hunky Fiona, that's a technical term, really powerful one, and we drop shipped it at Berkeley to the headquarters of Jupyter and then to San Diego and then connected them at 40 gigabits a second. That provides a backplane for now extending it everywhere across not only the UC system but all of the different places. Now, how many of you are using Kubernetes? Okay, IBM up front, good. IBM's a good supporter of that as well. I had no idea what that term meant. It's Greek for pilot or captain. Until we started using it. One of our wizards brought it to my attention, John Graham. This is one of the most important software innovations that I've seen in my lifetime. Google developed the first real planetary computer. So data centers all over the world. Now, it's also Microsoft and Facebook and AWS and so forth, and many of the banks and everything. But fundamentally, you've got this problem I'm dealing with in the cloud. It's the basis of the cloud. You have all of these distributed computers, that have to act like they're one. When you go searching, you're not searching this, you're not logging into this data center over in Netherlands or this one over here, you just want an answer, right? So they found a way in software to handle this. And the way they do it is they take all the applications, put them in what are called containers, and then those containers can just be moved around, and they have all the information they need to execute them on any computer. And so then they developed this thing called Kubernetes, which is a container orchestration software system that essentially allows them to put any executable on any machine and with no human intervention. And this thing, it's hard to believe it. It came out in basically 2 years ago. This is two of the people at Google, two of the wizards. It's just a way of stitching together all these machines into basically a big computer. Where have you heard that before in the last 15 minutes? Okay, so the cloud has already done what we're talking about doing in the academic world, and then everything at Google runs in a container. This is the world of 2017. And so I really encourage you to get to know about this. I had to. And this is just from Christmas Day. All of the industries are joined in on this now. There are probably 40 at least different companies, including IBM, that are supporting this, including all of the cloud providers as well. Now, this is a little bit technical, but now that we've got that software to do the containers, you've got to do storage, okay? And again, the miracle of open source, Rook is this open source thing that takes object storage, and the emergent one that everybody seems to be using is Ceph, and essentially all of the storage on all of the computers is now all orchestrated by Rook under Kubernetes. And I know this sounds a little technical, but you got to know this stuff. This is the distributed fabric of the world today. And it is why the world works. And if you're going to build things like applications on top of it, this is the sort of thing. So finally, here's what, 2 years ago, we finally got to the nirvana that we've been going after for 30 years. On all these distributed computers, which you can see here are everywhere from UCSD to Caltech, Stanford, Berkeley, and so forth, we have these Fionas that are called digital transfer nodes, and then they have the storage, Ceph storage on them, and then they've got all of the Kubernetes is organizing the movement of executables in these containers all over this thing. So this is one computer to first order, even though it's totally distributed. And it's so tightly coupled that you might say, well, Larry, if you have all these big data, you're not going to be moving these big datas all over the place. That would, that's crazy. Well, the whole point is, think about it, if you got a cluster over here, its backplane is running at say, 10 gigabits a second. If it's connected wide area at 100 gigabits a second, the data here and the computers here are already co-located. It's just a question of speed of light latency that's left. But you were already doing that. If you, in architectural terms, any cluster is a non-uniform memory access cluster. That means from this computer to this computer to this computer on the cluster, if you have to use a piece of data that's on this memory, this memory, this memory, it takes a different amount of time to get it to the CPU, non-uniform memory access. Well, now, if you have one that's at Stanford instead of at UCSD, it's just a little bit more of a way to go to get the data, but you already are in that game. So from a software or an algorithm point of view, it doesn't really matter. You're all in this one big computer. Okay, that's enough about computer architecture. What about the applications? So I started as an application scientist, and I had to learn all this computer stuff. But fundamentally, think about any given big science team, astronomy team, particle physics, Large Hadron Collider, biomedical data. We've been talking about even visualization, earthquake engineering. Imagine you're a professor and you're in some campus, right? And you've got some data. You don't have all the data. You've got collaborators at other universities, and they've got data, and they've got data, and then there's data in a national repository, then there's a big supercomputer over here, then there's your cluster, then there's, you know, your personal computer. I mean, it's all distributed. So I went out, malice aforethought, to find my users who were already collaborating with other people at different institutions over the normal internet. And I said, okay, would you like to be part of this experiment? And we'll give you 1,000x increase in your bandwidth connecting your collaborators and all your data and everything. And then the question is, how does your science change? Well, here's an example of the Large Hadron Collider, which generates an unbelievable amount of data every second, distributes it to thousands of researchers all over the world. This is a trace of the speed going from the cluster on the 3rd floor of the physics building at UCSD all the way to Fermilab in Chicago. And you'll notice the scale over here is 30 gigabits a second sustained. Whereas before, over the shared internet, you might get 30 million bits a second, right? So this is using the Pacific Research Platform for particle physics. I had no idea what the aggregate demand for, say, cancer data is. So one of the big revolutions in science in terms of fighting cancer is not to think of it as you've got ovarian cancer or breast cancer or brain cancer or whatever. It's a software disease. So this cancer cell in your body somewhere was previously one of your human cells. And so it had a DNA that was like the DNA in all your other cells. Then it got mutated. Where? What was the mutation? Was it inversion? Was it a duplication? Was it a, okay. So the revolution in the last 5 years has been to go through and find out in that 6 billion bases of diploid DNA, what exactly kind of software failure did you have? Where in your code did you have somebody pull out a go-to statement and put in, you know, an if-then? And so all that data now from each patient is being put together by the NIH into a national database, which was at the San Diego Supercomputer Center. Well, then you can imagine everybody who is in an oncology practice wants to download that data to compare it with their local patient that they've got. And so here over 2012, 2013, and 2016 is the aggregate download. And you can see by the time of already January of 2016 is 2 years ago, it was peaking at 15 gigabits per second sustained. That's why you need these kind of networks. So then the NIH finished that project and it moved to Chicago, but it turned out we, of course, had been working with Chicago as part of the PRP, so we just sent up Fiona to the new place at the University of Chicago, and we continue. So this allows for the kind of flexibility that you see when federal agencies change where they're going. Well, I mentioned distributed virtual reality. We've been doing that for 30 years. That's what I did a lot of my keynote on back 7 years ago. And so we are building virtual reality facilities around, here's one, for instance, up at UC Merced, UC San Diego. We put them tied together by the optical fiber, and we can now move 2 gigabytes a second in 2 seconds. So essentially, you can have people in these distributed spaces that are in the same virtual space, but at a resolution maybe 100 times an Oculus Rift, which is the head-mounted display that Facebook now is selling. So this is like, you know, what you'll have in your commercial consumer VR in 10 years or something. Somebody may have noticed last winter that it rained a lot in California. These are called atmospheric rivers. And the study of where the atmosphere condenses out water and then dumps it on the ground is a very essential thing to understand at a time of sustained global change. Because we are a water planet, and that's where almost all the heat is stored from the CO2 that causes global warming. And it changes the evaporation rate, and most of the changes in the weather will actually be in precipitation events. So we have a center at the Scripps Institution of Oceanography, and they're in a big data collaboration with a Center for Hydrometeorology at Irvine. And they were using the regular internet back and forth. We put Fionas at both ends, put them on the Pacific Research Platform, and a workflow of moving big data from, say, something, the Irvine one is following all the precipitation events worldwide, and then the one at San Diego is then looking at the West Coast out to Arizona and how that, things like atmospheric rivers or droughts happen based on where the rest of the world is. They were taking 20 days for an entire movement of data before they could do one unit of science. That's now down to 20 hours, which means instead of once a month making a unit of science, they can now do once a day. And when we get it up to 100 gig point to point, it's going to be down to 20 minutes. That means you can make that same amount of science happen once an hour. So it's really transformational in that sense. Now the thing we learn is as soon as you have all this hardware, then you got the software, then you got the applications, and it's all big data, the next thing they come and tell you is, now I gotta have machine learning. And this gets to what we heard in the keynote yesterday. So one of the things they do is each of these precipitation objects is born somewhere, develops, like think of a thunderstorm developing, it's moving across the plains, and then it has a tornado, and then it finally goes away, or a hurricane or anything else. That's a space-time object. So they actually keep all this stuff in object stores like Ceph, and then can do machine learning to figure out, well, where do the precipitation events in the world actually mostly start? But it's a machine learning on these big object stores. And then the second thing on our campus is I'd been putting this fiber optic everywhere. Well, I went to the Scripps Institution of Oceanography, which has this famous pier in La Jolla going out. Well, we said, well, why stop at the pier? Why not put the fiber in the water? And what that allowed them to do was to put microscopes on the fiber to look at the phytoplankton in the ocean, and they now have over 300 million images that they've generated in the last year or two. And so they came to me and said, Larry, we need machine learning now to figure out who's who. I mean, we're not gonna, I mean, you do remember in the 50s, right, that they used graduate students to look at bubble chamber photographs that they now make like, I don't know, 100 million per second at CERN. So I presume they used to use graduate students for this, but in this new world of big data, that's not going to work so well. So we put a new NSF grant to say, okay, we went back to NSF to say, oh, we just forgot one thing. We got to put machine learning on top of this specific research platform. And so we got a new grant that just started in October. And we went out, remember, I had all these 20 or 30 campuses, I got all these different application people, but the one thing I hadn't talked to was a computer scientist. But I knew all these people now. So I went back to the campuses and I say, are any of you guys interested in machine learning? Have you heard about that? And so I ended up with 30 faculty from 10 different universities, Berkeley, Caltech, Stanford, UC San Diego, and so forth. They said, yes, and we're doing this kind of algorithm on this kind of architecture. And so, again, they volunteered to be part of this project. But it's very interesting, you know, in machine learning, Caffe is the most widely used university-developed open source library for machine learning, and Professor Trevor Darrell at Berkeley was the head of the team that developed that. And we went to him and he said, well, what do you guys need to actually amplify, to accelerate your work? And they said, well, GPUs is what everybody's using, but there's two kinds of GPUs. There's the gaming GPUs that they sell, 50 million a year. And then those are 32-bit. And then there's the 64-bit ones, which are like in all the supercomputers and Amazon Web Services and so forth. They're quite expensive compared to the gaming ones. And I'm not telling you this, Professor Trevor Darrell is telling you this in a quote he allowed us to put in the proposal, that basically that's what you need for machine learning, maybe even 16-bit, in some cases even 8 bits, because the data that you're machine learning on has such uncertainties in it that if you're doing double precision arithmetic on it, you're fooling yourself that you're getting something that's more accurate. Now, there may be situations where you actually need that extra accuracy, and by all means, use 64-bit. But he was saying that what we in the computer science community and universities are missing is gaming GPUs. And so I went back and I scratched my head and I said, but don't our Fionas, our PCs, have slots in them? Turns out we can put, don't you put gaming cards in slots in PCs to do gaming? So we can put 8 of these. These are the top of the line NVIDIA, or at least they were last 2017. But we can put 8 of these in, and now you have a kick-ass machine learning big data analytics platform. So 1 year ago, I went to UCSD and I said, well, if this is what the top people in computer science, Berkeley, are saying, what do we have in the way of that at UCSD? And they said, gaming GPUs, that would be the goose egg, 0. A year later, we have 350 of them. We have them that are set up in the Open Science Grid for applications with the San Diego Supercomputer Center. Our newest cave has 70 of these things just to drive the graphics. And most of the time, we're not looking at anything. So, and they're connected at 40 gigabits a second. So that's an awesome machine learning thing. The grant itself is going to put another 90, almost 100 of them. And then we went to our CIO and said, let's see, we have a master's program in data science now. We're starting an undergraduate program in data science. Where are the GPUs that you're allowing the students to learn machine learning on? Where are they? Oh, you don't have any. They got with the program. Now we have nearly 100. And that'll go much greater this year. So the GPUs, what are graphics processing units, were built to accelerate graphics, have, of course, become what you're using to accelerate machine learning. But they're von Neumann architectures, the same architecture that we've been using for 60 years to build computers out of. However, it turns out that I would say the biggest trend in hardware right now is non-von Neumann machine learning accelerators. This is just taking off everywhere because machine learning, as we heard yesterday from the keynote, is everywhere. If it's at everywhere, then we better have more computing power to execute all that extra machine learning. Well, are we going to do that on von Neumann processors alone? Well, here's the deputy director, Horst Simon, who's a colleague of mine for 30 years in supercomputing. Quote he says is he believes that we'll merge to a hybrid model. So any petaflop supercomputer now doesn't have just multi-core CPUs. It's also got GPUs. That didn't happen 10 years ago. The need was to accelerate computationally intensive things, and so that's why they put the GPUs in. But now that machine learning is going to come together, because in the next generation of supercomputer we're building in this country called the Exascale, the call from the President of the United States, the former President of the United States, I might say, said that in the architecture, you're going to make data analytics just as important as traditional solving partial differential equations, high-performance computing. Well, that's a little different. That's never happened before in the design of a supercomputer. So we're going to have to add the machine learning into the supercomputer itself, and that's why these non-von Neumann things are going to be important. So 2 years ago, I went to our top machine learning professor, Ken Kreutz-Dogato, and said, it looks like we're going to have to put together a lab to study all of this. And so we're now not just looking at deep neural nets, we're looking at all these different ways, these are all just different classes of machine learning algorithms. And we're going to start looking at the non-von Neumann architectures. Now, IBM, again, was a pioneer in this, and Dharmendra Mota, who was a graduate of UC San Diego School of Engineering, this is the cover of Science in 2014, and this is a brain-inspired architecture, a non-von Neumann architecture. And you'll notice that in that article, Dharmendra says, you know, we don't just have single chips, but we have on the drawing boards multiple parallel versions of that. Well, the next year in 2015, Lawrence Livermore Lab collaborated with IBM and built a 16 processor version, and now the Air Force has a 64 processor. So this is, in just 2 years or 3 years, done exactly what IBM said it was, brain-inspired computing chief scientist. So, almost done. The final stage in building this national global scale big data analytics machine is to surround the Pacific Research Platform with the von Neumann GPUs on it from this grant with, for instance, the 64-bit ones, and NSF has a number of supercomputer centers that have those, but then the clouds. The Amazon Web Services has all the 64-bit. Google has its non-von Neumann, what are called TPUs, that accelerate TensorFlow, which is its open source software for machine learning. Microsoft has the FPGAs, field programmable gate arrays, that it has put in every server to accelerate Bing search. IBM has both the True North that we talked about, but it's also got its IBM's cloud platform and Watson that we'll be linking in. And then there's a whole bunch of startups like New Edge and Nirvana that Intel recently bought, and others that are building non-von Neumann machine learning accelerators. So where are we going with all this? Well, last August, just a few months ago, NSF had us hold the first workshop, brought 150 people together to say, how can we take this from the Pacific Research Platform and make a national version of it? And we're having a series of workshops this coming year to follow that up. But my last slide I want to show you with is that this is from the birth been global. So in addition to the US version, the Netherlands, which has been a long-time partner of ours, has been in this, is in the proposal. Australia, Japan, Korea joined, and we just recently had a Fiona in Korea doing 5 gigabits per second, disk to disk, across the Pacific. So the fact that it's high bandwidth and long distance no longer matters. We've been able to get around that problem. And Guam, we just put a Fiona ad, and Singapore, we just sent one to. So this is all the same kind of, all within the same rack, global scale. Okay, so I would just leave you with this. You know, it took us 30 years. I'm 69, I'm not gonna be around to help you guys figure this all out, but now that we finally have this tightly coupled global scale thing that includes extensions into the cloud, Kubernetes extends into all the clouds, what are we gonna do with it? How are we going to get application people to actually move over to it? That's a very big problem. I didn't have time to get into cybersecurity, but there's a lot, this is a lot more secure than things that are attached to the normal shared internet, but there are a lot of issues there. Yes, we have multiple 10 gigabit links into AWS, and we will certainly into IBM and to Google soon. That doesn't mean they've got the internals like we have, the Fionas and so forth, that do the internal tight coupling inside the cloud complex. That's unsolved so far. But how, I mean, look, we've got 20 or 30 universities. There's 200 self-identified research universities in the United States alone. I mean, there's 40 or 50 here at this countries, you know, at HICSS. So how do we scale this? It is not really an engineering problem anymore. Yes, there are some details, but it's fundamentally a social, political problem. And that's where I will leave you. Thank you very much.
I guess it's quite mind-blowing, but just I wonder how much time you sleep every night.
8 hours, if I can do it.
Good for you.
I actually measure every heartbeat, and I measure every moment I'm asleep. So that's 8 hours sleeping, and it takes about 10 hours in the bed to do that.
Chief, can you say something about Exascale?
So the question for those out in streaming land is, can I talk about Exascale? So the way that supercomputers go, I remember the first megaflop computer, million floating point operations per second. And then when I bought the Cray 2, that was the first gigaflop. And then the first teraflop. And then nowadays, they're in the tens of petaflops. And so the United States is committed to making an exaflop computer, which is 1,000 times a petaflop. First of all, it'll be very interesting whether the United States makes it first or whether China does. And the other is, will it really be new technology, or will they just squeeze everything in the current version so that they can just get over the gate, you know, over the finish line and say they've done an exascale with 10-year-old technology? That's the most likely outcome. It's not the most interesting one. But the other thing is, you know, oh my God, as a person, as a guy who's done supercomputing for 40 years, you know, trying to talk about a supercomputer like it's a big thing anymore, you know, I mean, each of these is way more powerful than a Cray 2, and there's a billion of them. And I mean, I don't know how much the cloud providers add a year, 100,000, a million of these. I mean, that is where the world's computational supply is, not in individual supercomputers. And in fact, one of the big challenges, I think, really big, almost cultural challenges for supercomputer centers is to get rid of the center and get into the real world and integrate. And that's what the beauty of this with Kubernetes, it integrates the supercomputer centers and the clouds and the clusters and the PCs and the instruments. It doesn't really matter because everything's in a container and just running around in this you know, highly connected space. It takes a lot of re-engineering your brain to think in this space. And I got to give it to the cloud providers. I think they have attracted a whole new generation of people who can think this way and who engineer stuff at a scale that is just beyond anything any of us have ever imagined doing. And they do it at a level of customer satisfaction and reliability that is superhuman. I mean, it's just amazing to me how incredibly engineered this world is. So what we're trying to do is to make sure the academic world doesn't get totally left behind. I mean, the problem is the cloud providers are this giant sucking sound that is pulling all of our leadership out of faculty and so forth out of the universities. Well, who's going to teach the next generation of students if everybody's working for a cloud provider? So part of the motivation for this is to get the academics working on a system that is in some ways more powerful, although different in the kinds of data that it looks at than the cloud providers, and one that integrates very smoothly, you know, with the cloud providers so that we can all lift our boats simultaneously. Yeah, one question back. So I've lived through, as I said, each of these 1,000-fold increases, starting with the mega flop. And as you say, the reason it's so difficult, like, remember vectorization? So when the Cray 1 came out, it wasn't the first vector machine, but it was like at the labs. There was a year-long strategic vectorization exercise before the Cray showed up. And that was to take all the codes and to, you know, like interchange the I's and the J's and the do loops so that you could use the vectors to speed things up instead of just run on the scalar. And so it was a whole year of just software engineering to get ready for this. So it is, as you say, it's the hardware and the software and the application codes, all of them have to go to a whole new level of change. And when you get to the exascale, you know, it's like 1 billion gigaflop machines. So think about what the error rate is in one of these, and now multiply it times 1 billion, and it's going to be like the ENIAC, you know, where you had to go around with people changing vacuum tubes all the time because they were burning out if we're not careful with fault tolerance. And that may mean that you have a whole new set of algorithms that are fault tolerant. They just say, well, one of the computers in this million that I was running on, you know, or 10 of them or something, you know, randomly just went dead. Or you know, whatever, gave bad answers. But I've got to have an algorithm that's tolerant to that. I mean, after all, biological systems work that way. If you had to have everything perfect to 13 digits for every cell in your body, for every biochemical, you'd all be dead. Well, maybe on that positive note, we'll stop. Thank you.